let's see on the spot if I could come up with some, not formal, informal kind of proof of p-series. So what I'm thinking here is, right, we know the integral test, right? We use the integral test when, continuous, positive, decreasing, those three criteria, right, they're followed within, the interval that we choose. And integral test, I don't really need to do a proof for that, since integral test is, and by the way, feel free to skip this if you're done with the problem. I don't know, I like to put a twist on things, because that's what makes math more interesting. What was I about to say? Yeah, integral tests, like, the best way to kind of conceptually understand it for now is like, in Unit 4 when we learned about integrals for the first time, it's like we first talked about the Riemann sum, infinitely many rectangles, that relation to FTC, and just that gives us the gist of like the series can behave like the integral, right? Or the integral can behave like the series, kind of, right? So that's why integral test works, okay? Just because of that relationship. So, and we know integral test, we use it a bunch, so why not just use integral test, right? So what I'm thinking is, firstly, we can say here that just the expression 1 over x to the p, right, it would be continuous, positive, and decreasing. But this would only be true, right, if x is greater than or equal to 1 and p is greater than 0, right? Because then would not be in p-series form otherwise, right? So then we can now, since we did the justification here, continuous, positive, decreasing, we can therefore apply integral tests. So we can say here, improper integral from 1 to infinity of 1 over x to the p. This would then be the limit as b approaches infinity, 1 to b of 1 over x to the p dx, and this should be dx. All right, and so let me think like a programmer here. Let me put like an if and an else. All right, so we can say if p equals 1, because if p equals 1, then we can't use power rule. We'd be dealing with natural log. So we would then have limit as b approaches infinity of natural log absolute value of x from 1 to b. Now we technically don't need the absolute value, but we can keep it. Just better be safe. And so then we would just have limit as b approaches infinity of ln of x, or of ln of b, and then this would just be infinity, so divergent. So now we just have our else. So for all p-values that don't equal 1, what will happen? So now we can just use power rules. We'd have limit as b approaches infinity. We can rewrite 1 over x to the p as x to the negative p. So then we just have x to the negative p plus 1 over negative p plus 1 from 1 to b. I hope this works. This is just me thinking here. So then we can say here, right, if negative p plus 1 is greater than 0, right, just think about the exponent here, it would be very top heavy. And again, the reason why I'm prematurely making these conditions on p, and you're like, oh wait, do the FTC, why aren't you doing the FTC with b? Well, it's just because you're plugging in b, and that's not really doing anything, right? The behavior of the p would still be the same. So that's why we can just set the conditions for p here without doing any FTC or anything, because that would just remove the p entirely, and we're trying to find conditions for p because this is p series test. So anyway, if negative p plus 1 is greater than 0 here, just think of it like an exponent. Like, this would be very top heavy. So this would just go to, like, if we had like a limit here as p approaches infinity of just this guy right here, this would just go to infinity, right? So this would be divergent as well, right? So now, what if negative p plus 1 was less than 0? Okay, so now we'd be dealing with like negative exponents, and yeah, this would not be infinity. This would be converging, right? And so now we have divergent, divergent, convergent, right? So now I'm just going to rewrite these inequalities here. So this should be, right, this would be p equals 1 divergent. Move the p to the other side. This would be p is less than 1 divergent. Move the p to the other side. P is greater than 1 convergent. So you can say, therefore, very vague here, convergent for, and we're going to smush this all together, p equals 1 and p is less than 1 divergent, right? So we can say for p, or we want convergent first, for p greater than 1 and divergent for p less than or equal to 1. I think that's, again, very informal, but I think we got the job done. Let me know if I made an error here. Again, this, I'm guessing this, this is not like officially part of the video. This is just a fun thing. But I think everything checks out. Again, not formal at all, but yeah, let me know. Thanks for watching if you made it this far.